Okay, it's time to learn more facts about SN2 and SN1 reactions, the substitution reactions that we just talked about in the previous video. Let's focus on SN2 reaction. S stands for substitution and for nucleophilic, and 2 is the order of the reaction, so we call it SN2 reaction. We will reach to that point that we explain the order of the reaction. Everything happens in one step, so 2 is for the order of reaction, not for the number of steps. It happens mostly with the primary or some less hindered secondary alkyl halides. You will see why, because everything happens in one step. The molecule shouldn't be that hindered, so the nucleophile can attack and leaving group leaves right away. So here what it happens. Nucleophile attacks the electrophilic carbon. The electrophilic carbon is the one attached to the halogen. Then there is no intermediate, but it's a tetrahedral, like more than tetrahedral intermediate kind of thing, which is not an actual intermediate, and the leaving group leaves. The fact about the SN2 reaction is inversion of configuration. So one more thing here about the SN2 reactions is that inversion of configuration happens. Means if the molecule was chiral and it's an R configuration, at the end of SN2 reaction it changes to S. If it was an S configuration, it will change to R. So for example, let's say halogen is our first group, primary group. This is the second one. This is just random. We're just showing that for the understanding purposes. So the least prior group is in the back. The rotation is clockwise. So this is an R molecule. If we number the groups the same way again, so we will have, here, 4, 3, 2, and 1 will be your nucleophile now. So the rotation is going to be counterclockwise this time, and it's going to be S. Why it happens? Because a molecule should be open as an umbrella, and you see this is opening, so we will provide enough space for nucleophile to attack the electrophilic carbon. Because there is only one step, and in this one step, both nucleophile and alkyl halide are present, so the rate of reaction depends on the concentration of both alkyl halide, which I show as Rx, and nucleophile, first and first. So this overall reaction is second order. Didn't we say it's a second order reaction? That's why it's called SN2. There is no intermediate, so there is just a kinetic energy diagram is like this. There is no intermediate. And I will jump to page 7 to talk about some facts about SN2 reactions. 7. As far as the substrate, as far as the alkyl halide, we said the primary is better than secondary, is better than tertiary. Of course, the less hindered secondary, the better. It's a backside attack. As far as the nucleophile, nucleophiles' strong bases are better. Strong bases, better. So from left to right and down in the periodic table, the nucleophilicity increases, is better, improves. And of course, negative nucleophiles are better. So H2O is less than CH3CO2. And you have the sequence. I'm not going to waste the time of the video for that. And so on. As far as the leaving group groups, the weaker the base is, the better the leaving groups. So strong bases like OH, NH2, OR, they are less suitable as leaving group as fluoride, chloride, bromide. So these strong bases are worse leaving groups than the halogens. And the best leaving group is this ion. We call it tosylate, TOS. You will learn more about this tosylate in organic 2 when you have, for example, something like OH and you want to change it to a good leaving group, so you change OH to OTOS. Wait until you reach there, but this is what you need to know. So for nucleophile, strong bases are better. As a leaving group, weaker bases are better. And finally, as the solvent, they are better in polar A product solvents. So the transition state here is going to be stabilized better by polar solvents. But if you have a product solvent, it might have a side reaction with nucleophile. So it's going to interfere. If you have product solvent with a hydrogen, it's going to react with your nucleophile instead of letting nucleophile does its job. So A product solvents, but polar, are better for SN2 reactions. So these are the facts about SN2 reaction. Let's talk about SN1. SN1 reaction is totally different from SN2. Again, the facts. It happens in 2 steps. And 1 here means first order. We will reach there again when we study the mechanism. And it's suitable for tertiary alkyl halides when there is the electrophilic carbon is too crowded. So we say it happens in 2 steps. Like let's say, for example, an alkyl halide is tertiary. Is it? Yes. Carbon connected to chlorine is connected to 3 more carbons. So there would be no nucleophile, even the smallest nucleophile, that can penetrate inside the molecule to attack the electrophilic carbon, or it will take a long time with a very low efficiency. So in the first step, the molecule spends energy. That's the slow step, because it takes some time for a molecule to get rid of the leaving group. So slow step or rate determining step, general chemistry 1. So what happens is there is a carbocation. We call it carbocation. It's a cationic carbon, so we call it carbocation. And it's a tertiary carbocation because the carbon carrying the positive charge is connected to 3 more carbons. A tertiary carbocation is formed, and in the second step, step 2, the nucleophile attacks. So, depending on which side of the molecule has 2 sides, depending on which side the nucleophile attacks, it can form one of the configurations. So you will have a racemic mixture. instead of inversion of configuration that we had for SN2. Now the reaction forms a racemic mixture when it is applied. So depending on if you consider this carbocation as, let's say, this, then so depending on excuse me, if nucleophile is attacked from this side or this side, then it will form two different and if again we determine we label the priority of the groups, we will have R and we will have S. So we will have racemic mixture. But one more time about SN2 reactions. We have one step for second order, and it's good for especially primary alkyl halides and some less than their secondary, and inversion of configuration. But as you see here for SN1 reactions, there are two steps. It's first order reaction. Why first order reaction? Because we said that we write the rate law for the slow step. In the slow step, do you see any nucleophile? No. So the rate of the reaction, the rate equation is written as this, and this is just first order. There is no nucleophile entering in the first step. So there is an intermediate here, so you see the activation energy for the first step is much higher because it's a slow step. It's activation energy of the first, activation energy of the second step. So activation energy of first step is much higher than activation energy of second step, making the first step the slow step of the reaction. Jumping to page 8. The factors that affect the SN1 reaction, we said tertiary alkyl halides are much better than secondary and primary. As far as the nucleophile, because the slow step of the reaction includes only the alkyl halide, the type of nucleophile does not have that much effect. As far as the leaving group, the same as SN2, H2O, weak bases are the worst. And again, tosylate is the best. And finally, as far as the solvent, is the opposite of SN2, polar and protic. Polar, protic. Polar because the polarity stabilizes the carbocation, the intermediate. And we need normally protic because there would be no, again we said, because nucleophile is not going to be in the first step, which is the more important step in this mechanism. So proton on solvent does not do anything on the nucleophile, and it's not important for us. So mainly when you have a polar protic and tertiary alkyl halide, that's the sign for an SN1 reaction. Ready to work on some exercises? Yes, you learned the facts, keep them in mind, review them, and let's work on page 8. I will work on we're supposed to draw the product of nucleophilic substitution and determine the likely mechanism. So, which one is our nucleophile? This is a nucleophile. Which one is electrophile? This one. What type of alkyl halide are we dealing with? The carbon connected to chlorine is connected to 3 more carbons, so it's tertiary. Tertiary alkyl halide. And what type of? A nucleophile is strong, so for tertiary alkyl halides, the reaction goes through SN1. The product, the final product, is not asked for the mechanism, the final product of the reaction is going to be a substitution of chlorine with OCH3. Feel free to draw the mechanism. For C, you have a strong nucleophile because it has a negative charge. And you're dealing with a secondary alkyl halide. It's not that hindered because this ring is planar. And so for secondary alkyl halides, it's a little bit tricky to determine SN1 and SN2. Here, since you have a strong nucleophile and it can penetrate inside the molecule, so most likely SN2 is the dominant mechanism. So the product would be the substitution of iodine with, call it ethoxide. All right, some more exercise on page 9. Not going to work on everything, but just to give you a clue about each one. Again, I would like to work on A and C. In the first exercise, you are supposed to determine the mechanism of the nucleophilic substitution, draw the product including stereochemistry, and draw the mechanism. So whenever it's applied, we need to show the stereochemistry. It's a strong nucleophile, and you have a primary alkyl halide, so it's a recipe for SN2 reaction. So there is the attack from nucleophile to electrophile. Here, let me just not put too many arrows. And the bromine will be kicked out. You will have O and the rest of the molecule plus bromide. It's important for you to write it. For C, seems like you are dealing with what? You have a tertiary alkyl halide, so you will have an SN1 reaction. The molecule first needs to get rid of its iodine because it's too crowded here. And then CH3 OH is going to attach, so it's going to form OCH3. But there is a positive charge here since the lone pair was spent for the formation of the bond, or you can easily determine the formal charges. Then what happens is that, oh, there's a hydrogen here. The second molecule of solvent, again, we don't just have one molecule of methanol. The second one comes, grabs the hydrogen, leaves the electrons on oxygen to stabilize the charge on oxygen. OCH3 with 2 non-bonding electron pairs. That's the final product. I'm sure you can work on B and D. For the next exercise, still working on page 9. Let's work on B. Determine the mechanism of nucleophilic substitution of each reaction, then draw each mechanism and draw the products including the stereochemistries. For B, seems like stereochemistry is shown, so we have to follow that. What type of alkyl halide is it? Secondary. Nucleophile is a strong, so it's calling for, and the solvent is aprotic solvent. So our nucleophile won't be distracted by the hydrogen in the solvent. We can proceed to SN2. The molecule is going to have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So molecule will have the opposite stereochemistry. We have R here. We will have S. Yeah, opposite. Inversion of configuration for SN2. And let's work on F. It's a secondary alkyl halide. Was not a very strong nucleophile. So seems like SN1 is a little bit more dominant. For SN1, molecule spends energy to get rid of the halogen. Nothing happens to the methyl group here. And then CH3, CH2OH. Then you have, let me draw it here. You have either this or this, right? Depending on where oxygen attacks from. Because we're supposed to, for SN1 reaction, we're supposed to have racemic mixture, right? Then now the second CH3, CH2OH molecule helps the first one to stabilize the charge. Don't forget we have methyl groups here. So we have OCH2, CH3. And we have, of course, we have some byproducts, but don't worry about them, please. So this is our first product, and this would be our second product to form a racemic mixture for us. Don't know why I keep forgetting these methyl groups. This is a racemic mixture. All right, congratulations on finishing SN1 and SN2. If you pay attention to the last part, you just have started synthesis of the organic compounds, which is a big area in organic chemistry. You can synthesize, you can make new molecules from initial molecules. The first practice, and I'm only working on the first practice. Second practice, I prefer to wait until the end of study guide 8, until the end of chapter 8. So, the first practice, how can you prepare diethyl ether? You can look it up online for the structure. from an alkyl halide and any other organic compounds. So, seems like if we have this, we have a strong nucleophile, right? So the rest of the molecule should come from alkyl halide, correct? So on the arrow, I have this. What should it be connected as we use as the alkyl halide? 2 carbons connected to a halogen, chlorine or bromine. So it's going to go through an SN2 because it's a primary alkyl halide. And then chlorine will be kicked out. The final product is going to be, isn't it? So this is the beginning of synthesis reactions and synthesis of organic compounds. Buckle up to be able to successful. Don't be afraid of synthesis. If you know the alphabets, if you know the reactions, you will be getting the synthesis reactions. Just needs practicing and not to be disappointed or giving up. All right, good luck with the studies for this chapter. Don't forget the end of the chapter questions.